Hello, my name is Travis Monk. This is one of a series of videos on ecology. This video will focus on population growth, specifically the math behind these calculations. The video on population ecology introduced population size, density, and growth. This video will focus in particular on how to measure population growth in general, as well as how to use two different models of population growth exhibited on this slide, the logistic and exponential models of population growth. Populations, as exhibited in the previous slide and described in the notes on population ecology, can increase or decrease in size. One possible way that a population can change in size is when individuals are born or when they die. The growth rate of a population can be calculated by taking the number of individuals that are born minus the number of individuals that die divided by the total original size of the population. An example problem involving this concept will be shown later. Populations can rise or fall in other ways, such as people migrating into or out of a population, but population growth, as we discuss it, will merely be a calculation of number of births and number of deaths as they relate to the total size of a population. Just as rates of immigration and immigration can vary significantly from country to country, the same is true for population birth rates. What this graphic depicts is the number of births in each country per 1,000 people. If you were to look at the age structures of these different countries, you would find a strong correlation between the percent of individuals in their primary reproductive ages and the total number of births per 1,000. Many developed countries, such as the United States, Sweden, Russia, and Germany, have very low birth rates. Russia was so concerned with their low birth rates in recent years that the government declared a particular day a national holiday, gave everyone a day off work, and promoted, with prizes sometimes worth thousands of dollars, the idea that people should go home and make babies. Countries like China, on the other hand, with large population growth rates, have instated policies to try to lower these growth rates. There are two different models for population growth that will be described in the next few slides. What these models of growth attempt to do is explain how a population with a positive growth rate increases in size over a period of time. The exponential model, shown on this slide, describes how a population can grow in conditions where there are no limiting factors. While this model is not realistic long-term, what is observed is very rapid growth rate. The larger the population gets, the faster it increases in size, as suggested by the greater and greater slope in this graph as time goes on. Examples of this type of growth would be observed when the human population has grown over the last 250 years, as well as bacterial growth on a petri dish, short-term. There are three different equations that are used for different calculations involving the exponential model of growth. First, you may need from time to time to calculate the rate of growth, or R. To do this, you can just subtract the number of deaths from the number of births in a given period of time and divide it by the size of the original population. If you know what the present population size, N, is, and multiply it by the growth rate, or R, you can estimate, after 1 unit of time, usually 1 year, what NF, or the future population size, would be. You may sometimes want to estimate the future population size many units of time, or T, into the future. As opposed to repeatedly using the second formula over and over, you can take the previous growth rate, 1 plus R, to the T power. Examples using each of these equations will be described in the upcoming slides. The first problem involving exponential growth explains how to calculate the rate of growth of a population, or R. As this equation suggests, you need three pieces of data. Number one, the number of births per unit time, or B. Number two, the number of deaths per unit time, or D. And third, the total population size, which is N. This problem asks, if you had 900 births and 300 deaths in a population of 2,000, what is the growth rate for this particular year? All that you need to do for this problem is to plug in the three pieces of data provided here and solve. The three different variables, births, deaths, and population size, are all designated here in red and point to their appropriate space in this equation. If you take 900 minus 300 and divide this total by 2,000, you would arrive at an answer of 0.3. Written as a percentage, this means that the population has a growth rate of 30%. You must always use the decimal form of a percentage in these types of problems. The second example problem incorporates the growth rate, or R, that we solved for in the previous problem in an attempt to project what the population might look like in the following year. NF in this problem represents the projected future population, NP represents the present population, and R, as stated on the previous slide, represents the population's growth rate. This problem asks, if this year's population is 937 and the growth rate is 3%, what would be next year's estimated population size? There are only two variables that you need to find the answer to this sort of problem, R and NP, both of which are provided on this problem and designated here. The present population is 937 and the growth rate is 3%. Again, percentages must be written as a decimal form or you will arrive at the wrong answer. After plugging in these calculations, the estimated population size after 1 year would be around 965. The third exponential growth formula follows the same principle as the second, but can be used to predict the growth of a population over many years as opposed to just one. The t in this equation represents time. This problem asks, if this year's population is 937 and the growth rate is 3%, what is the estimated population size in 11 years? The first thing to do in this sort of problem is to plug in the three variables that are needed for this equation. The starting population, NP, is 937. The growth rate in decimal form, R, is 0.03. And the amount of time, or T, is 11 years. Plugging all of these values into the equation, you would expect to find the starting population of 937, growing at a rate of 3%, to increase to about 1,297 over a period of 11 years. This exponential growth rate model can not only be used for ecology, but is also used in determining interest earned on principal investments. The logistic model is a more realistic representation of population growth because it takes into account limiting factors to a population. These limiting factors, which could be food or nesting space, for example, act to suppress or push down the population size. The largest population that an environment can sustain because of these limiting factors is called the population's carrying capacity. As you can see in the graphic to the right, no population can increase in size forever. This model of growth, the logistic model, shows that while the population can increase in size very quickly over the short term, as the carrying capacity comes close to being reached, the growth rate, or slope of the line, begins to level off. There is only one equation for logistic growth that we will be working with, that is provided on this slide. You may notice that many of the variables used for this equation are the same as those that were described earlier on the topic of exponential growth. The notable addition is K, the carrying capacity of the population. The only example problem for logistic growth asks, if the human population on Earth is 8 billion and the carrying capacity is 9 billion, the current population has a growth rate of 2%, what would be the expected population size next year? The starting population of humans on Earth, NP, is 8 billion and is found 3 times within this equation. The growth rate of the human population, R, is 2%. Written in decimal form, this should be 0.02. Finally, the carrying capacity, or K, is 9 billion. This is the last variable that's found twice in this equation. When you plug all these values into the equation, as shown on this slide, you could expect the population of humans on Earth to be 8.017 billion, an increase of 17 million next year. That is the end of this video exhibiting how to mathematically calculate population growth. If you're interested in learning more about ecology or any other themes of biology, please subscribe to my channel. Thank you.